All right. Well, building an accuracy flywheel for your LLM RAG apps. Quick introduction. My name is Puneet. I am one of the co-founders and CEO at AIMon Labs. My background has been in leading teams, building products from 0 to 150 million ARR at companies like AppDynamics and most recently at MuleSoft. I have here my co-founder and partner in crime, CTO of AIMon Labs, Preetam Joshi. He's built personalization systems, recommender systems at Netflix, led data science teams at Thumbtack, and contributed key components to search systems like Yahoo. We also have on the team, not here today, Vivek and Alex, who come from Stanford AI Lab and NYU. Their experience has been in researching topics like LLM alignment, as well as graph databases and similar other topics. And we are backed by Bessemer Ventures and Tidal Ventures and some other amazing angel investors. All right, so this presentation is completely about this super happy, excited developer on the left bottom of your screen because he just got a new LLM RAG chatbot to build from his manager. But soon he realizes that there's a lot of ups and downs in that journey. There's a lot of learning and a lot of issues to resolve. Number one is, I don't know if this is okay or too noisy, but number one is getting the right data into the RAG system. Who do you need to work with? That data is probably not available all the time, right? Then there are issues with the data. For example, noisy data, conflicting information, incomplete data, all that. Let's say he gets to a point where he is sufficiently happy with what he has, and he now has to figure out how to index that data into a RAG database. Number one thing is he has to select a RAG database. Of course, Milvus, right? From there onwards, he has to figure out what embedding models to use, what chunk size to use, and all that stuff. So he has to set it up for it to work. Well, how does he check it? He checks it with wipe checks to start with, tunes the database metrics, but then he realizes that to serve real queries, he has to figure out query processing. Maybe too much data is retrieved. He has to figure out how to trim that data down, filter it down, re-rank it, consolidate it, and this is not the complete list, right? And then he has to figure out how does he monitor the relevance of the retriever, the whole RAG system together. Well, let's say he's happy. He pushes all of that data into the LLM output for each query, and voila, LLM still hallucinates. Well, why? Because LLMs are probabilistic systems. They can hallucinate still, even if that happy developer is doing everything right. So at the end, we have a developer. I tried to make it look sad by some paintbrush tools. Has a greasy laptop, a lot of coffees down. Well, TLDR, the manager is not happy. Customers cannot trust the chatbot, right? Well, he's not alone. We have talked to many such developers who have been struggling with, getting this entire pipeline work properly for like 6 months, 8 months, and more. And this is an example of a hallucination on one of the iconic FANG companies that we all used last weekend to order a lot of stuff on Black Friday. One of my friends was trying to return shoes, and the chatbot was suggesting her to press the power button, adjustment button, and those kind of things. All right. So let's try to talk about root causes of these inaccuracy issues, right? So,
maybe hold the microphone a bit further away.
Bit further.
Yeah.
You can still hear me?
Yes.
Okay, revolution. Okay, so pre-generation, data issues, pre-generation, processing issues, and then issues with LLM generation itself, right? So we talked about missing data, conflicting data, etc. We talked about choosing the right embedding model, the type of RAG you use, re-ranking, etc. But then LLMs might still hallucinate. How do you select the right model for your data, for your use case? How do you get a grip on fabrications or if hallucinations happen in real time? when your apps are being used. So, well, people use LLM judges. It's a very popular approach, both for grading the relevance of your retriever, which is basically the output of your entire RAG, and then the overall output of the system from the LLM, right? But inherently, there are problems with LLMs when used as judges. Well, they're not built to score, to grade. They're not calibrated. They're not consistent to do that. We have an example on a blog post on our website where we have the same query used twice with GPT-4o Mini. First time it says the score is 4. The second time it says the score is 7, right? They could be subjective. And then I think high latency, cost inefficiency are pretty well-known drawbacks of using LLMs. So what do we do? Well, first, I need to level set and take you through this workflow because I'm going to use parts of this diagram to talk about the flywheel. So very quickly, we have data from different data sources, processed, indexed, chunked into a vector database. Like Milvus, query comes in, finds the right relevant matches, data is fed into the LLM, and then most people we have talked to use RAG to serve the user queries, but then there's a good bunch who are using fine-tuning as well, right? Okay, so we define a flywheel as a process that helps you continuously improve the entire RAG LLM system. Part 1. Well, everything starts with data. So what if there was a solution that actually looked at all of your context and gave you all the different areas where you have problems, right? Problems like noisy data, conflicting information, those kind of things. And you could get a data set that you used to improve your entire RAG LLM application. That is definitely going to help improve accuracy. Part 2, this is pretty interesting. For RAG relevance, people use LLMs. We talked about some of the drawbacks of using LLMs, but what if they were purpose-built relevance graders? Well, definitely better than using zero-shot or few-shot LLMs right off the shelf, right? Well, I think we should do better because my definition of relevance could be different from yours. My data is different from yours, right? So those graders need to be customizable to adapt to your definition of relevance. And then taking it to the next level, we need to have a way to incorporate user feedback. It could be internal user feedback, developer user feedback, but also end user feedback, right? Is it a good or a bad response from the overall system? Now, imagine if you have a really good data set about positive examples, negative examples from your retriever. You could actually then use them to fine-tune your embedding models and your re-ranking models as well, completing the flywheel here, right? Which is going to help you increase accuracy quite a bit. Now, applying the same concept to this third part, if we talk about the output from our LLM, and we are able to offline and also online, real-time, monitor it for whatever matters to you, right? Hallucinations, instruction adherence, any custom metric. And imagine you are able to create a data set using that, using human input as well as automated models. That then you can use to preference tune your LLM. Now, automatically is going to learn stuff like, does LLM mean lunar landing module for your business, or does it mean, the law degree, etc. And I think the fourth part is prompt optimization. I'm not going to go into this too much. I think there's a lot of open source. There are a lot of open source libraries and resources around this, and a lot of people are investing a good amount of time on this. So I didn't really talk about what we do. So we are helping our existing customers and design partners build out these flywheels. We started by building some proprietary models that are the core that actually help you figure out these issues. For example, hallucination detection model, instruction adherence, and context quality. We just today put our hallucination detection model, HDM1, on Amazon Marketplace. And this is a model that beats all other accuracy, hallucination detection models in terms of accuracy and in terms of latency, and gives you GPT-4o level accuracy in much, much lower latency. Okay, so we help you evaluate, figure out what these issues are, track the performance in a nice UI, and then help you troubleshoot when your hallucination rates go up or your RAG relevance drops, and then complete the flywheel by helping you improve the different subsystems of your application. With that, I'm going to hand it off to Preetam to go over an amazing demo.
Yeah. All right, let's see. All right.
You were able to figure it out.
All right. Thanks, Puneet. Okay, so let's see. I have about 8 minutes, give or take, and I'm going to go over this demo really quick. If anyone wants to follow along, you can go to this URL here, which is this AIMon-ZWS. This doc is also linked with our documentation, by the way, so you can always find it on docs.aimon.ai. So very quickly, what are we going to do here? So we're essentially going to use Milvus and Llama Index and AIMon to build a RAG-based chatbot to chat with our documentation, which is basically docs.aimon.ai, right? And I'm going to show you how you can use these three systems together to basically build an amazing LLM application. So this is the high-level architecture of how we will be building this app. So essentially, you have the ingestion component here, where you have a Llama Index-based crawler, and that's where AIMon comes in to check whether the context that's being ingested into Milvus is actually good or not, and we'll talk about that in a little bit. And then we have the inference component, which using your LLM application and Milvus, we essentially be able to retrieve the most relevant document for a given user query, and we'll validate whether the response was good or not, right? Yeah, so the only two things that you need here is an OpenAI API key and obviously an AIMon API key. For this exercise, we'll use Milvus Lite, right? So let's go ahead and start building this. So some very quick environment variable setups. This is where you would configure AIMon, and I want to introduce this concept of detectors here, which Puneet was alluding to, right? So in this case, at the ingestion stage, we will use something called as the context classification detector, and we'll name our application whatever here, and the model that we'll be using from OpenAI is GPT-4o Mini, right? So let's go ahead and do this. And these next set of functions here are pretty simple. All they do is look at a sitemap, they crawl documents from there, extract text from these URLs, and then ingest them, right? So let's go ahead and do these as well. And it'll take about 6 or 7 seconds. Yeah, and once that is done, we will basically go ahead and use the AIMon detector, and all you have to do is use this decorator here, super simple. And then let's see what it came up with, right? Like, so this is the detector, and then in this case, if you go to this is the UI here. It found a few items that were conflicting, and let's just look at that very carefully, right? This is obviously manually simulated, but this is for this demo, I essentially injected some fake documentation into our site. So over here, this snippet suggests that HDM1, which is our flagship detection model, has some subtle knowledge gaps and whatnot. And then over here, it talks about misclassifies outputs as hallucinations. So clearly, these two pieces are conflicting, right? So that's one way you can detect this. It also gives you a text-based reasoning. And again, these are proprietary models which run under low latency. So let's go ahead and remove that conflicting piece of documentation. And then the next set of steps are pretty familiar for you all, right? Like we'll use an OpenAI-based text embedding model. And let's go ahead and generate embeddings and store them into Milvus. So this is using Milvis's Llama index integration. So once we go through that, essentially what we have done so far, so that's already done. As you can see, it's created the index. So this part of the ingestion pipeline has been realized so far, right? And I'm probably 2 or 3 minutes into the demo. So the next piece would be creating your inference pipeline. So pretty straightforward there. Using the index that was built, we would basically configure a retriever, which is again a Llama index retriever, configure our system prompt. We'll skip over the details here. Like I said, we'll use OpenAI, GPT-4o Mini with a temperature of 0.1 because we don't want it to hallucinate. At least that's the hope. And then we'll go ahead and use the retriever query engine, right? So let's go ahead and do that. And then the last piece of finishing this diagram that I showed you at the very beginning is to configure an AIMon detector. Right. In this case, as if you remember, initially at the ingestion stage, we only had one detector, but here we'll have our hallucination detector, a conciseness, completeness, and also something called instruction adherence. Essentially, what instruction adherence does is it checks whether your LLM followed all of your instructions properly. Typically, in many use cases, you would have told the LLM to do X, Y, and Z, and it would only do X and Y, right? So that's sort of one of the bigger problems that people face when building LLM applications. So let's go ahead and do that. And then the next step would be, this is just an ask and validate function. It's just invoking some, the query engine. And then there's some helper functions to basically get the context document for which is required from AIMon, right? Okay, so the first question, how does AIMon solve the problem of hallucinations? I've also asked it to explain it in technical terms and limit the response in under 500 words. So let's go ahead and run that really quick. And then let's see the response of the LLM. Probably takes a couple of seconds here. Right, so it says the AIMon addresses hallucinations by utilizing its proprietary hallucination detector, which evaluates the LLM against the provided context to quantify any factual inaccuracies or fabrications, right? So this looks pretty good so far. And this is AIMon's judgment of this. So essentially, we have a completeness score, which seems pretty good. We have a pretty low hallucination score, no context quality issues, as you can see. And instruction adherence was great as well. So both of these instructions were properly followed. So we've finished building this entire thing. And if you go into AIMon's UI, you'll be able to see something like this, where you would see all of these detectors with just one little decorator that you have configured, right? So last thing, which I'm going to go over really, really quickly, is we'll simulate a hallucination here. And in this case, we're going to ask it this question where, give me the full set of labels that the toxicity detector generates. Now, for this purpose, for this demo, I actually removed the toxicity detector from our documentation. So it's going to essentially say that this particular response is hallucinated, even though the LLM will attempt to answer it with something, right? So it says the labels are toxic, abusive, offensive, hate speech. Now, in theory, this thing looks great, right? But it's actually not correct. These are not the labels that we have. So what we're going to do is actually ingest the documents that I had excluded at the very beginning. I'm going to update the vector store, right? Like, this is pretty cool from Milvis. I can update it really, really quick. I'm going to reassemble the query engine. And then I'm going to reissue the query just to see what happens there. And then in a couple of seconds, okay, so these are actually the labels that we produce. And you can see that there was no hallucinations here. So we went through the whole process of detecting conflicting information during the ingestion process. We went through a query where we simulated a hallucination using Llama Index and OpenAI. We detected this hallucination using AIMon in super low latency, under 300 milliseconds, and we fixed it. So that's all it is from me. Thank you so much for having me.